Okay, today we're going to be talking about circular motion, so get your notes out. We have going to start off with a demonstration. Newton's first law, if you remember, is inertia, which basically says that an object tends to stay in the same state of motion unless acted on by an outside force. So if object doesn't have any outside forces on it, it either is at rest or it's traveling at the same speed in the same direction. Now we start to talk about circular motion in this chapter. All right, something's traveling in a circular motion, all right, like the stopper on the end of the string. What can you say about Newton's first law?
It's correct.
All right, well, first law says that an object that has no net force on it will either be at rest or will travel in a straight line. What about something that travels in a circle?
So straight.
Circles are not straight.
Consistent.
So it's not a no net force, right? There's got to be a force for something to travel in a circle. All right, so write that down in your notes. All right, there has to be a net force for something to travel in circular motion. All right, now I want to take a minute and think about that net force. As far as the requirement of that circle, and I had us doing a horizontal circle, but just to take a look at this, put it in a vertical perspective. What is required for that circle to continue to move? We need the stopper to be traveling at a certain speed. If we slow down, what happens to our circle? And we end up losing our circle, right? So that it has to have a certain speed. And what's another requirement of it? What's holding it in the circle?
A string.
All right, the string. So I initially said that there are things that are at rest or in traveling at constant velocity in a straight line. There's no net force. So something that's traveling in circular motion, there always has to be a force. In this case, the force is the string. The string's pull on it. You guys remember what that force is called? When a string pulls on something? It's called a tension, right? So there has to be a tension. There's got to be something pulling. And in what direction is that pull?
Downward. Circular.
Let's see. Let's kind of draw a picture of a circle. When the stopper is here and it's moving in that direction, what direction is the tension?
Upward.
Well, it's toward this way, isn't it? Look at where the string is. It's pulling towards the center. All right? When the object gets to this point and it's moving in this direction and the string is this way, which way is the tension out?
Center.
Center. All right, so for something to travel in a circular motion, there's always a force pulling to the center.
It's
All right,
like gravity.
that's something we notice about circular motion. We're always looking for the force, and in these kind of 3 points of time, the tension's always to the center of the circle. When it gets around here, object's moving this direction, the string is in that direction. All right, we always get the tension going to the center of the circle. So this demonstration kind of sets up circular motion. You're always going to look for a force that's pulling to the center of the circle. All right? That force, whatever is producing that force, that net force is called the centripetal force. Centripetal force, and that's the force that's directed towards the center, directed towards center. It's the force that keeps the object traveling in circular motion. And we each actually even have a formula for centripetal force. The equation for centripetal force is F. We can put a sub C if we want to. That might help us to remember this circular motion. Centripetal force is going to be equal to mv squared over r. All right, m is going to be the mass of the object. V is going to be the speed, not the velocity, speed, because the direction's constantly changing. All right, so we're just interested in the magnitude of how fast it's going, squared, divided by the radius of the circle, and that's our formula for centrifugal force. All right, now, what I want to expand our look today on circular motion and look at examples of and kind of describe what's going on. And I'll make a little bit of a table if you guys can put that in your notes. On the first column, I want you to put the word example, and we're going to look at several examples of circular motion. On the second column, I want us to try to think through what is the force that's produced by circular motion. All right? I'm going to make 4 columns. The third column, I'm going to put free body diagram, put together a free body situation we're looking at. And then in the fourth column, I want to put an equation to express what's going on in that circular motion. All right, so this will be an analytical look at different examples of circular motion. We've already set up the dynamics of circular motion. If there's always a force directed to the center of the circle, that net force is going to be equal to mv squared over r. Just to verify that there is a force there, I have in this demo that we just looked at before, the circular motion of the stopper, but in the other end of the string goes through a holder, and actually there's a hanging mass that's at the end of that string. Notice the hanging mass doesn't go down. So apparently there must be some force that's keeping gravity from being able to pull that. In other words, we could possibly find the magnitude of that force going down and make it equal to the centrifugal force of the tension in the string. All right, so there is a quantity there, and it is in fact a real force. And we see here in that example, because of the speed of that, the stopper is producing enough tension to hold up that hanging weight. All right, let's go for the first example. It's the one we just did. Let's do the stopper and string. All right, stopper and string. Example. All right, what was the force that we say? Tension in the string is what kept it in a circular motion. Free body diagram. Well, as far as the free body diagram, if you want to carefully analyze the free body diagram, there's 2 forces acting on it, on the stopper. Well, what were the 2 forces doing? Well, we said the tension, that's kind of going to the inside. And what other force is acting on the stopper? Gravity. You notice that I put that tension a little bit above the horizontal? And the reason for that is, if you looked carefully at my demonstration, the stopper actually was a little bit lower than horizontal because there's not another force to push it up. If we put that stopper on a frictionless surface so that the normal force would be equal and opposite to the mg, then we'd have a horizontal situation. Here, because of the situation, there's only the mg going down. The more tension I put on this, the longer this vector gets, the closer it gets to be horizontal. All right, that's the free body diagram for the tension. Yes?
Is like the normal force still there?
There is no normal force because it's not resting on a surface.
Oh, right.
It has to be on the surface for us to have a normal force. All right, so our equation here would be simply T, that physical force is producing all the centripetal force necessary to keep that in circular motion. That's going to be equal to mv squared over r. So that was fairly easy. All right, second example, car on a curve. I'm going to put car on an unbanked curve. All right, as far as an unbanked curve, looking at a car from behind as it's going around the curve. All right, as the person goes around the curve, and say they're making a left-hand turn, going on a left-hand curve here, what force is actually pushing it? We know that there has to be a force, right? There's got to be a quote-unquote string in every situation, right? The string that held the stopper and kept it from going off in a straight line has got to be pulling to